Hi, my name is Greg. I'll be teaching a little bit of introductory heat transfer and thermodynamics.
And I'm Mario Guerrero. I'm Thermal Team Lead, and I've not taken those classes yet, so I'm very interested in learning about it.
And now you all get to learn this stuff. So, we're going to start off talking about different heat transfer methods. Well, we're really going to start off with some of the basics. Some of it's going to be review, and then we'll get into the methods of heat transfer and how you calculate it. God, this is already going terribly. Oh well. Temperature is just how much atoms wiggle around in their structure. So if something has a higher temperature, then it wiggles around a lot faster. And there's a lower temperature, it wiggles just a little bit. So, let's get into the first law of thermodynamics. Energy can't be created or destroyed. And energy of the universe is always constant. So we have thermal energy. Thermal energy. We have nuclear, chemical, mechanical, potential energy. Energy can move between different types, but it never gets fully destroyed or never gets converted into something that isn't energy. So, the second law of thermodynamics is a bit more difficult to understand. Let's just talk about the...
What is the second law of thermodynamics?
The second law is that the entropy of the universe can only increase. That probably doesn't make much sense to you. It doesn't make much sense to most physicists, but
can you define entropy?
No, I can't, and most people can't either. Some people say it's an amount of disorder, but that's not really the case. It's a better definition.
A pile of ashes is more orderly than a piece of wood in a campfire, but
something like that. Yeah, I don't like the disordered definition, because if I have all my clothes piled neatly in a pile, there's no difference in entropy of that versus if I just scatter them out. At least not from a
physicist perspective.
Not from a mechanical engineer's perspective. Technically, there is some, but we're mechanical engineers, so for all we're concerned, entropy is just a number, and you can look it up. Here's the entropy of nitrogen at this temperature and density, yada yada.
Now, what uses would an entropy value have to a mechanical engineer?
Some processes are isentropic, so that means entropy stays the same. This is nice because, it helps you determine what the end state is from a starting state.
Okay.
So if you have a perfect turbine, for example, you have high temperature, high pressure gas going through it, it'll drop in temperature and pressure. And if you know the outlet pressure, you still need something else to figure out what the outlet temperature is. But if you know the process is isentropic, you can look at the starting temperature and pressure, density, or whatever, and say, here's the entropy of that state. And then you can find that entropy in just a table or in a program or something at the low pressure that you want. And then that'll give you all of the properties of the gas you need, or vapor, or whatever. Entropy, it has the symbol of S. I don't know why. It doesn't.
Like many symbols.
Yeah. You got entropy, you got enthalpy, which is H, you got internal energy, which is U, and then there's just energy, which is E. And there's different types of energy. We just talked about that. Thermal energy and kinetic energy and nuclear potential and chemical potential, yada yada. So a better definition of entropy is how spread out heat is. So if you got two chambers right next to each other, and one of them is very hot, and the other is cold, blue, and you then open up this, say you have gas in there, nitrogen or whatever,
Sure.
What happens when you open this up? What'll happen to the gas?
Well, from intuition, the hot would flow towards cold.
Yeah, so it heat by definition transfers from hot to cold.
Oh, by definition as well.
Yes.
Okay.
Yeah. There's weird things with that, but for the most part, yeah, the temperature here and the temperature of the molecules, on both sides, it will slowly even out over time until all we've got is a lukewarm gas in there.
Okay.
And none of the gas is especially hot and none of it is especially cold. But
So is coldness just a magnitude of heat?
yes,
Okay.
it's entirely relative. You can say, oh, your forehead is very hot, you must be sick, when when your forehead is considerably colder than, for example, the sun. So hot and cold are just a general measure of a relativistic kind of thing.
Gotcha.
So this is a more disordered state by definition. So in the process of opening these two chambers, we have created entropy because the heat has become more spread out.
And there's no way to reverse that entropy, is there?
Correct. There's no way to
before.
reverse that.
Then how did we make two hot chambers at different temperatures?
We'll get to that.
Ooh.
So
Primer.
One of the other important things with the second law is that pretty much all energy slowly moves towards heat energy. So if you've ever heard of the heat death of the universe, that is when the entire universe has kind of run out, as they might say, and everything is now the same temperature. And since everything kind of tends toward temperature, then there's nowhere else we can go. There's nothing else that can happen. You can't make a new region really hot because there's no way to gain electricity from heat specifically. Now, you can create energy from a heat difference. So if you have, for example, really hot gas and a really cold environment, you can create what's called a heat engine. And doing that,
Oh,
you can
I
take...
think I've seen one of these before.
You've seen a million heat engines, don't worry.
Okay.
You probably don't know. It's basically you take the important thing is that to make energy you need two different places. A source and a sink. And the way you create energy is by allowing thermal energy to move from the source to the sink, and it will output some energy in other forms. It could be electrical, it could be mechanical, generally electrical. Usually goes into mechanical first and then electrical, but the problem is that you are now cooling down this section and heating up this section. If you do not have a sink to cool it down, you get no energy out of it. Similarly, if you don't have a source, if you only have a cold sink and you don't have a source of heat, you can't get energy out of it. The importance is that there's a difference. And during this whole process, you are creating entropy. And for that reason, energy runs out, basically. So if you have, say, geothermal energy, you can heat up water, get it very hot, and then run it through a turbine and get your energy out. But in doing that, you are cooling down the inside of the Earth, and it eventually will cool down too much so that we no longer have a source, and then you don't have any energy. So I guess the important thing is that heat engines, you have to create entropy to get energy out of it. And that's a one-way direction. You can't reverse it. You can't reverse it. That would destroy energy.
Similar to how you can't, certain processes you can't chemically reverse.
Something like that. I don't know enough about chemistry, honestly.
Okay. Well, it's hard to unburn a log in a campfire.
Yeah. Yeah. But,
Or fossil fuels, you can't unburn those.
yeah, I mean, you can convert it back into carbon, which is technically the case, but
wow.
it takes a lot of energy to do that.
Gotcha.
Which is why no one does it.
Nothing in physics is for free.
Yeah, pretty much. So, if you have another energy source, say you already have a battery charged, you probably got that somewhere from heat being transferred between two things.
Wow.
But you can move heat from a hot space, or from a cold space to a hot space. So I'm going to draw that again. I guess another good thing to note is you can also have heat transfer between hot and cold area just by nature, and you don't have to get energy out of it. So if you take for example, you could take a cold soda can or cold beer, and you leave it out on the table. Now it's colder than the ambient environment, so thermal energy goes from the environment into the can, and the can will warm up, and the room temperature will slightly drop, but not very much because there's not a lot of thermal mass there. So you don't need to be able to get energy out. The kind of the crux of this is that a lot more energy is going this way than is coming this way. So if you then take that energy and try to pump heat from the cold region to the hot region, you can pump some, but you can't pump this much. And that's why it's a irreversible process, basically. But you can, if you have another source of energy somewhere, you can take heat and move it from cold to hot. But you must put energy in, otherwise there's no way to do it. And that's what a refrigerator does. So,
I think of it kind of like a right-hand rule, like. I mean,
I can draw these one on top of the other. It doesn't matter. Okay. It doesn't have to.
Doesn't have to come from the bottom there, but I just kind of see it like, yeah.
Yeah, we can.
Energy in, energy out.
Yeah.
Thinking of it with like axes, kind of.
I don't think about it with axes. It doesn't. The direction or the orientation of any of it doesn't matter. It's just where the arrows go from and to.
Okay.
So if I draw cold over here, I don't know, then I can draw it like, hey, over here, energy in, and yeah, don't worry about the direction. It's just that if you want to.
Just remember what's required for each state.
You're required to put energy in to make this happen. You can have these two states by their lonesome, doesn't matter, but you can't manage the movement of energy this way without inputting considerably more energy, and that's why. So let's look at a refrigerator.
All right.
So your hot space is just the room. Room temperature. Boom. That's room temperature. It's probably like 20 C or something. I don't know. And you have a space that's also room temperature inside the refrigerator, and you want to cool it down. So when you buy the refrigerator, it's not pre-cooled or anything. So what you do is you apply a refrigeration process. There's a couple, but the vapor compression cycle is the common one. But basically it starts moving heat from that space to this space using energy. And as it does that, this section cools down a little bit, and then it keeps cooling down until you get to whatever temperature you want. But the important thing is that since energy is conserved in here, what can you tell me about this amount of energy?
It's going to be much higher than the energy that
Yeah, so
would be cooling the space.
yeah, so it's higher.
So more
than
goes
this.
to the room than inside the refrigerator.
Yes. In fact, the amount of energy here is equal to this plus this.
Oh, so half.
Yeah, because you're removing heat energy from here, and then you're adding electrical energy. So it's not actually half, but it's a sum of the two, basically.
Oh.
Usually, in fact, this is pretty big. For room temperature refrigerators, it's actually pretty efficient. You can have a pretty low amount of energy in to get a decent heat transfer, but if you're trying to get really cold, like dry ice or liquid nitrogen or something, this energy becomes massive. And it gets a lot worse as you get colder. Or as this temperature gets colder. So let's just dry out our refrigerator real fast. So you've got a compressor. It's just one small compressor. It takes gas in, pressurizes it. But in this process, it also tends to add some heat to the gas. Just when you compress something real fast, it tends to warm up also.
Yeah.
You can, if you do it really slowly, you can do it without the temperature rising too much, and that is more efficient. But it takes a lot more time, and it's just not really worth it. So.
And that's why you hear a little buzzing noise.
Yeah.
Go up close to your refrigerator.
Yeah, it's the compressor. Let's see. Yeah, so you compress it. High temperature, high pressure. In fact, it's warmer than the ambient room. So then you take that and you put it through a heat exchanger of sorts. In the
And we're
room.
using the symbol for a resistor.
Yes.
Electrical.
Sometimes they use
stuff like
heat
that.
exchangers with the same resistance.
What would be the difference between heat transfer and heat exchange?
Exact same thing.
Oh.
So this is just a type of it's a piece of equipment that's designed to exchange heat, and it's designed to do it very well. So then we have this goes into the room. This pipe, it comes out the back of the refrigerator and has a few coils or something. And that's just sitting out in the room. In fact, if you look behind that refrigerator, you could probably
It's hidden behind the little panel, but I know it's there.
yeah. Anyways, so it's hotter. It's hotter than the room. So which direction does heat flow?
Hot to cold, correct?
Yeah. So is it flowing from the refrigerator into the room or from the room into the refrigerator?
From the refrigerator into the room.
Yep. Heat leaves the system. So I should probably also draw an energy input into there.
Maybe write out the equation for heat transfer.
We can get to that. We barely even started on here.
Okay.
We just know that some heat is leaving the system. So now we have a system that is medium temperature, room temperature, and high pressure. Because since there's like a constant pipe going through here, the pressure hasn't dropped at all.
Sure.
So, and there's another mechanism. So one nice thing is that so if you compress a gas and you compress it quickly, it heats up and it increases pressure. If you then release that and allow it to open again, the pressure drops and the temperature also drops.
Okay.
If you're to do that right here, and both systems were completely 100% efficient, basically, you would get back down to the same pressure and temperature you started. Exactly. But we are now at a lower temperature.
Ooh.
Lower temperature than that. So, if you cool it, if you allow it to expand, you get to, I'll draw this in a second, a lower temperature and low pressure. So now you are colder than the room. So that's kind of what you need for refrigeration. Now there's a couple different ways of making this process. The simplest one is just to use what's called a throttle valve. It's basically just a valve that's just slightly cracked. So it has a restriction in it. so it's very difficult for the gas to get through it. Because of that, the gas has to speed up to the speed of sound in that fluid, and the pressure is going to drop significantly across this.
I guess it's kind of like a reverse compressor in a jet engine.
A little bit like that. There is actually there's a more efficient method. Yeah, so this is basically just an orifice. So if you have a pipe going through and you have just a tiny little opening there, then assuming your flow rate is high enough, you get a massive drop in pressure across here, and then also a drop in temperature. But this is not as efficient as if we had expanded it in a turbine. So let's also add a turbine. Let's try that. So we have, let's see, this direction. So the gas expands going through it, and it also creates work.
Oh.
That's the important thing, because it's doing the same thing as the throttle, but it's also putting out work. So there's a temperature drop from the pressure drop, and a temperature drop from some of the work that got done. Now, this amount of energy is nowhere near that amount of energy. Thermodynamics makes it impossible, but it is some amount of energy. And the important thing is that you do actually need to make sure this energy is removed. Put it on, give it a motor, make some electrical energy. Mm-hmm. But if you just let it free flow, it's just going to turn back into friction. You're going to lose that energy from friction, and then it's just going to heat this up again. So then you'd be back to the same place with the throttle. But the thing here is you now have a moving part in the cold side. It's going to get very cold inside this turbine. And the difficulty is that makes it a lot more likely to break.
Okay.
And so for that reason, household refrigerators don't have turbines. They just use the throttle valve. Super cheap, pretty much never breaks, no moving parts, yada yada. So it's not as efficient, but it's useful. Then we go into the refrigerated space. We have another heat exchanger. It is very cold. So if you start off with at room temperature in here, you now have gas coming in that's lower than room temperature.
Would they change the pipe diameter to expand the gas?
You can. It's not the.
You'd have to recompress it to go back into the loop, though, right?
Yeah. So.
Yeah. That might not end up being more efficient.
Yeah. So the main thing is that you're now taking heat from this space
into the
removing it, and now that causes the gas or the liquid in here to warm up, and then finally it'll leave. So now it's at medium temperature and low pressure. And then it gets compressed again and the cycle repeats. So this is why it's called a heat pump, because it's as if you are pumping heat from here, from the inner space out of the room. So that is the general process for how a refrigerator works. Really the only two things you need to know are that heat moves from hot to cold, and that you compress a gas, the temperature and pressure increase, whereas if you expand the gas, the temperature and pressure decrease. And then when you take Thermo 301, you're going to learn about how to actually calculate all this stuff. We won't get into that because we're not going to build a refrigerator, mainly because having a moving part in space is a pain in the ass. Let's oppose that to what if you want to heat the room? You have some sort of electrical energy source, and you put it through a resistor, like an electrical resistor.
Boy, that's a lot less steps.
Boom, you created heat. That's all you need. So now you can kind of start to see why creating heating is a lot easier and creating cooling is a lot more difficult. And that is why the heat death of the universe is going to be a thing. Because to cool something down, you need to add more energy to it than you're getting out, basically. So there's no way to run a heat engine and a there's no way to remove heat from a space and then also use that same energy to create energy to power the thing. And that's all the second law of thermodynamics. So, let's see. Let's move on to a little bit of calculations. So, if you have, say, I don't know, block of concrete or metal or whatever, and you need to warm it up a little bit. Say it's at 10 C, and you want to get it to 20 C. How much heat do you need to add to it to warm it up by that amount? So there's a nice equation, which is heat. Heat uses the symbol of Q. I don't know why. Is equal to the mass of it, because the mass matters. If you have a lot lower mass, then it takes a lot less energy to heat something up, times the C, specific heat of the substance. If you have a fluid, or if you have a gas, there's two different specific heats you need to worry about. For now, we're just going for metals or for solids and liquids. You can just have regular C, and then just multiply, and then by the change in temperature. So, say it's a kilogram, 1 kilogram, and specific heat is, I don't know, 1 kilojoule per kilogram Kelvin. And then change in temperature is 10 degrees. Now, notice this is in Kelvin, but we're using a temperature difference, so we can just use the difference in Celsius, because the difference in Celsius and Kelvin are the same. 15 Kelvin difference. Multiply it out, you get 10 kilojoules. So Kelvins cancel out, kilograms cancel out. You want to talk about the temperature scale a little bit?
Yeah, Kelvin scale. Not super familiar with
okay, yeah, no
I
problem.
haven't taken chemistry yet.
Oh, yeah. So, so that's really simple. This does not tell you how long it takes.
Ooh.
That's the important thing. In reality, it's going to be it's going to start heating up quickly to begin with. Let's say you put this in a space that is, that has enough heat of other sorts, maybe the gas is warm or something.
Sure.
Such that you know that as the gas temperature cools down and as the block temperature heats up, they will both eventually meet at 20 degrees Celsius, which is your goal. Temperature of the block over time, it's going to go from 10 to 20 degrees. It's going to go something like this. It's a logarithmic decay sort of thing. And if you look purely from thermodynamics perspective, it never actually reaches this line, but it gets infinitely close. So usually just say, how long does it take to get, I don't know, 95% of the way there, and then we'll call it good. Because realistically, if you measure it and it's pretty dang close enough. So yeah, it's a logarithmic scale, temperature scale, or a logarithmic over time.
Could you overshoot that to make it faster?
Yes. If you make the room particularly hot, say the room temperature is up here at 30 or something, 25, just because I drew it poorly, then yeah, it'll start going up like this, and it would go like that, up to there, and then if you take it out when it gets to this time, then boom, you're at that temperature. Yeah, if you want to heat it up fast and use at least this temperature, you can always overshoot a little bit and get there very fast. But for the most part, if you don't care too much about time, then you can just then you don't have to add as much heat to it to do that. Another thing to point out is the larger the temperature difference between the two substances, so the room starts at 25 and the block starts at 10, then you're going to have a larger, more entropy is created if the temperature difference is larger. So more waste energy, sorta. Don't worry too much about that now. But yeah, so how much you need to heat something up, it's just the mass, heat capacity, and the temperature difference you want to heat it up. So, is there any other questions on that briefly?
If it was a sphere, what would the curve look like?
Exactly the same. This isn't, I haven't given you a formula for this. Actually, the line I drew assumes that the whole thing is constant temperature.
Okay.
So there's, as soon as a little bit of energy touches the surface, the entire thing changes its temperature immediately. It's one of the simplifications that is common in thermo. But in reality, having a larger surface area means heat transfers more quickly. So if I had a sphere and a block of the same mass, and say, I don't know, a star of some sort that has a lot of surface area. So they have the same mass, so the formula I gave was exactly the same. It's mass, heat capacity times change in temperature. But the transfer of heat from one body to another has a lot to do with shape. So this has the lowest surface area, so it's going to be the slowest to heat up. This is a little bit more surface area compared to its mass, so it's going to be more medium, and then this is going to be a lot faster. Or alternatively, if you just had a powder, I keep dropping things. If you just had a powder, then that's going to be the fastest because it has so much surface area. So
That's why crushed ice melts faster than cubed ice.
correct. That's a good observation. We'll get more into how that works later. And then you'll have the formulas to make it actually make sense. But for now, that's a good starting point. Yeah, so as you know, the Celsius the Celsius scale has 0 as the freezing point of water, and 100 is the boiling point. That's completely arbitrary. We could have used ethanol, just pure alcohol, or something like that, but water's everywhere, and we figured it's a decent enough place to do it. So just take water at sea level pressure, and when it starts to freeze, that's the freezing point. When it starts to boil, that's the boiling point. And we basically defined our scale based on water. Now it's not currently defined that way, but that's how it was at the time. It gave them a really good way to make sure that the temperatures they were reading were the same, or calibrated the same anywhere in the world. But when they started looking at properties of gases, real gases as opposed to ideal gases. So ideal gases have the molecules have 0 volume. Makes it so that the temperature doesn't change a lot of properties. It's just a nice, easy PV equals nRT. PV equals nRT. So for an ideal gas, this is true. So pressure multiplied by the volume is equal to the number of moles of the gas, just literally how many molecules are there, times this ideal gas constant, or a specific gas constant. Universal gas constant, we'll just use that, multiplied by the temperature. I mean, if you drop the pressure, then the boiling point also drops. And I believe the freezing point also drops. I don't remember.
I think it would drop with it, wouldn't it?
I don't remember. So that's why they need it at sea level pressure.
Okay.
Even that varies a little bit, but they can measure that.
Yeah.
It's not too hard to measure. So they first started saying, well, if we were to compress this into a if we compressed it with infinite pressure, basically they start realizing that there appears to be a point where you cannot get colder. Now, if you talk to certain higher up physicists or thermodynamicists, they'll say, oh, well, you technically can get colder. We just have to use some weird quirks in the definition of cold. Fuck them. There's a limit called absolute zero. Now, we measure this to be about at negative 273.1 something degrees Celsius. So that's the point where you can't get colder than that.
And that would be 0 Kelvin, if I remember correctly.
Yes. So they said, well, we have this, it's kind of like speed of light. Cosmic speed of light is a cosmic speed limit. This is the temperature limit. You can't get colder.
Is there a limit in the other direction?
Sort of, but it's not something we'll worry about.
Okay.
Like in
Because
theory,
would it just stop being matter at that point?
pretty much. It's don't worry about that. It's so far off the scale of anything you will ever care about. Like it's massively hotter than the sun or any other thing that ever was. So don't worry about it. It's also not for the same reason. So
Interesting.
assume anything we're going to assume is going to assume that temperature can get infinitely hot. Don't worry about it. So they said, hey, we got the speed limit. It doesn't change anywhere. Temperature limit. Let's name that. Let's put that 0.
Okay.
So that's what we use for the Kelvin scale. So obviously you can expand the Kelvin scale to any temperature. It just means you always have a positive number.
Handy.
Kelvin. So one thing to note is if you're using ideal, pretty much anything ideal gas-wise, for the temperature you always have to subtract a certain temperature from it. You need to use an absolute scale, which is what we're using here. So because of that, they took the same same difference as the same amount of. They kept the unit size of the scale. They just shifted it down with this.
Oh, so it's the same. It's the same distance between each degree as Celsius.
Yep. So they made this
Distance.
positive 273 because there's a 273 difference there, and this is 373. So 100 difference, 100 difference. So it's literally just offset by 273. And this is how we currently define measurements of temperature. We no longer use water ice, even though it's almost exactly the same thing. But the official metric unit of temperature is Kelvin. So keep that in mind. And that's roughly negative 460 degrees Fahrenheit. And because of the importance of absolute zero, there is also a British unit for absolute zero called Rankine. Another important person like Kelvin. Yeah. So, if you ever use Fahrenheit, and someone complains that it's not metric, just tell them to fuck themselves because they're not using Kelvin. The true metric superiority is in Kelvin. So that's an important thing because when it comes to how material behaves and how particles interact, you're not going to get that with Celsius. You need Kelvin. So realistically, we should be using Kelvin just for everything. So if you're wondering, a warm day is about 295 Kelvin, and a hot day is something like 300 Kelvin. Usually in my calculations, I just assume 300, nice round number. It's around 70 Fahrenheit, or sorry, 80 Fahrenheit, and this is about 70 Fahrenheit. So when weather apps start using Kelvin, then I'll start using metric. my weather apps. Until then, I'm just going to stick with Fahrenheit. So that's the scale. And it's not too hard, just not going to get colder than that is all. Yeah. And then you can use this to determine differences to figure out how much heat is transferred, or you can use a comparison between two things to figure out which way heat is transferring. So heat transfers from the hot stuff to the cold stuff, but it then causes the cold stuff to warm up and hot stuff to cool down. So now you know what the temperature scale is. We're going to talk about how you change temperature of an object. You take the heat required to heat it up. Let's do this in black. Heat required to heat up an object. I use Q to represent heat. I don't know why. Equals the mass multiplied by the heat capacity multiplied by the change in temperature. So let's see. If we assume mass is 1 kilogram and heat capacity is, I don't know, 1 kilojoule per kilogram Kelvin, and temperature change is 10 Kelvin. For example, you have a block. With block, it's 10 degrees Celsius. You want to heat it up to 20 degrees Celsius. So a difference of from 10 to 20 is 10. Let's make it 10 to 25 just to be clear. So 5. Oh my God.
So I noticed that heat capacity has kilograms in it built in.
Yes.
So
we still need heat, or we still need the mass. If we already have these two combined, is a specific heat, I believe. And so that the units of that are just kilojoules per kilogram. Kilojoules per Kelvin.
Since it cancels out the kilograms.
Yeah, you already know what the mass is. So
okay.
That's if you have a single object you don't care about. So yeah, if you're raising from 10C to 25C, it's a 15 degree C change. And a change in temperature in Celsius is the same change in Kelvin. It's just offset by a different amount. So that's also 15K. One thing to note, you do not use a degree sign for Kelvin, because it's not a degree. Celsius uses a degree, Kelvin does not, so you do not say degrees Kelvin, you just say Kelvin. For comparison, you don't say, I weigh, I don't know, 80 degree kilograms. Doesn't make any sense, you say 80 kilograms. It's absolute. So just K, no degree sign for Kelvin. Anyways, run through this. So the temperatures cancel out, the masses cancel out, and that will give us with 10 kilojoules. So it takes 10 kilojoules to heat up a 1 kilogram block from 10C to 25C, assuming that is the capacity.
Wouldn't 10 to 25 be 15 degrees?
$15 kilojoules. It takes 15 kilojoules to heat up a block from 10C to 25C. It weighs 1 kilogram and has a heat capacity of 1 kilojoule per kilogram Kelvin. Okay. But this does not tell you how long it takes to heat up that amount. So that's something we're going to talk about later. But that has to do with how heat transfers. So, heat transfer. That's all we need to say on that. And then we'll just put in that other section. Heat transfer.
Okay. So we're stopping at conduction so far right now.
Yes.
Let's cover everything here.
Yeah. Let's say one other thing. So if instead you have a rate of heat change or something like that. Let's say you have say you have a pipe and fluid is moving through the pipe. and you know how fast the fluid is moving, and you know you need to get the temperature from here to here to increase. And so you're adding amount of heat to it. You can also use the same equation as a rate. So let's say you start off at 300 Kelvin. I just don't want to use Celsius right now, and you need to get it to 350 Kelvin. How much heat do I need to add to the system to get it to heat up? Because it's a continuous process, so it's not going to be just kilojoules. You could go for, if this process is going for 1 second, then it's considerably less mass than if it's a process going for 24 hours a day. Yeah, so, fluid going through a pipe, you need to heat it up by adding temperature. So, for that, we just use dots. So, heat transfer rate. So, whenever you see a dot and stuff, it usually means rate. So, in this case, kilojoules per second. That's important. So it's just a rate. Just black, it's easier to see. So that's equal to the mass flow rate times the C times the dt. So exactly the same thing, it's just the mass is in kilograms per second. And you need to know the mass flow rate here for that to work. So mass flow rate, heat, or heat capacity, excuse me, kilojoules per kilogram, K, and then K. Those cancel out, kilojoules per second, perfect. Nice. So if it's 1 kilogram per second, and you're transferring, I'll use the same times 1 kilojoule per kilogram Kelvin, and then multiply it by 50K, the temperature is increasing by 50K. We get 50 kilojoules per second, which has its own special unit of 50 kilowatts. So a watt is a joule per second. It's 1,000 kilojoules per, or 1,000 joules per kilojoule, and similarly 1,000 watts per kilowatt. So let's take joules per second. You can make a watt if you want. I usually just leave it in joules per second. Okay. Do other stuff. Yeah, so that's how you make it do something over time. If you don't, if you still need a amount of heat, and you can assume that the heat transfer is constant, then you can also do so we need heat. So Q dot is equal to Q over T, assuming the rate is constant. So Q is also equal to Q dot times T. So you can replace that. So if you have a constant heat rate, you can figure out how long it takes for the temperature to change at a certain temperature. Okay. So I'll rearrange this to dt is equal to, so if you know heat, the rate of heat transfer, and you assume that it's constant over time, and you know the time and the mass and the C, you can figure out how much the temperature changes. And that's one of the things we're going to use later for some of our calculations. If you doing that, you can figure it's going to help us later. Also, move on to the next thing. So let's talk about conductor. So there's 3 different methods of heat transfer: conduction, convection, and radiation. So, conduction is heat transfer through a solid body. It can transfer from two solid bodies if they are touching, but it is, but they have to basically be touching for it to work.
Would a medium like glue or some other binding agent count as touching?
It can be. It's going to be a mixture of that and convection. So it's through a fluid. So it's important to recognize that if nothing in the fluid is moving, so if it's I guess if it's a glue and the glue particles aren't moving around too much, then yeah, it's just conduction. But convection is moving, it's fluid motion that causes heat transfer. So technically, convection is a type of conduction.
Okay.
But it's just a simplified model for gases and liquids because trying to do conduction models with that sucks. So
would a good example of that be if you pour coffee in a coffee mug, and then it raises the temperature through convection, or would that be conduction?
If you have a coffee mug, let's just draw a mug here. Great mug. You're going to have there's at the surface of this there's going to be a conduction into it, and then through the coffee mug there's also conduction, but then inside the liquid it is convection. So the process of heat getting evening out through the liquid is the convection.
Okay.
So it's a mixture of
as the edges cool, convection is also occurring.
Yes. Let's see. Yeah, so conduction is pretty simple. Convection, there's two types of convection. There's natural and there's forced. So natural is what it is if there's nothing else moving the fluid. So the fluid isn't flowing already. There's no fan stirring it up or anything like that. In that case, if you a hot surface and then a cold surface, in gravity at least, heat tends to rise. And this tends to cause convection currents, which are kind of fluid tends to move kind of up and around. So it heats up and rises, and then it cools down and drops, and usually makes kind of currents of sorts. It could be in this direction, it could be a different direction, but the densities of the fluid are what's causing it to move. Because when it heats up, the density drops, making it rise. When it cools down, the density drops, making it sink. So that's natural convection. Forced convection is if it is moving for other reasons. For example, if the wind is blowing, that will cause more convection. So if you have wind blowing past the surface, then the convection of heat from the surface is going to be higher. So forced does not necessarily mean it's man-made. It should be clear. Man can technically make natural convection, so heating up. But that's just the way to describe it.
Then convection is for liquids and gases, correct?
Yes, liquids and gases. It's good to note that fluid means liquid or gas.
Oh.
It can be both.
Okay.
It can also be a supercritical fluid. Supercritical fluid is just it's a curious example of, basically it has properties of a liquid and it has properties of gas. This occurs when you are very hot and high pressure. High pressure? Yes. It's not particularly dangerous, it's not particularly hard to deal with. It's called supercritical because the density changes very rapidly as you heat or cool. And so if you're off by a little bit of if your measurement is off slightly, it could be a massive different. You get massive error bars basically. So it's super critical. And then the last one is radiation through photons. This is known as light generally. So there's different wavelengths of light. There's different energies of photons. Visible light is one type, has a specific wavelength between which we can see. And then outside of that, we just can't see it because our eyes don't pick it up. But there's more or less an infinite spectrum of wavelengths of light that we can see. And we'll get more to that later. Yeah, so we're going to be talking about more of these later. Let's start with conduction. And just how do we calculate it? So if you could flip the page. So if you've got how does heat transfer? So it's basically molecules that are jiggling more cause the molecules next to them to jiggle more. Just the heat or the energy in them starts kind of balancing out, and so basically they depart energy on each other, and the net flow is that everything kind of evens out. So from a kind of simplified perspective, heat moves from hot to cold. I told you that previously, although it's not the best definition anymore. The reason they originally said heat transfers from hot to cold, or even say heat transfer to begin with, is because they believed that heat was a type of particle, or something like that. You know,
like an elementary particle.
Yes, something like that. They call it, like, I don't remember what they called it, but they thought heat was a mass, and if I transfer heat to this board, they thought heat was a particle, and so originally they thought heat was a particle, and that's why they talk about it flowing as if it's a gas or a fluid or something. They literally believe that if I touch something with my warm hand, that some sort of particle is going to be moving from my hand into the colder board. Okay. That's what they believed. Slightly more accurate, but slightly more confusing, is that it's more of a it's an evening out of,
like a differential.
Yes, so it's like a gradient. So we got differential. So we got hot stuff versus cold stuff. I'm just showing like a density of heat. Temperature by position. So we have space that's hot and space that's hot and space that's cold. And the simplify. It's a difference. So you move along, heat change a little bit, and a little bit more, and a little bit more. It's a continuous sort of thing. And you could say that coldness transfers from cold to hot. The math works out. Don't use it though, they'll think you're an idiot. But the important thing is that it's a difference. There's a continuous change between the two. So if I have a block, one side's cold, one side's hot, I'll just add a little bit of color here. As you can probably imagine, there's going to be heat transferring through here. Again, it's just the way we say it. How much heat is that? Well, what do you think it depends on? Just in general.
I would think it depends on the difference between the hot and cold.
Okay, so the difference in temperature, yeah.
How resistant the medium is to change.
Yeah, good. Use that K. There's two more.
How much mass the medium has?
That's kept by that, sort of. But there is something else. If I make this super long, You think that's going to change things?
Yeah, it's going to make it much harder.
Yeah, it's going to make it a lot slower. So distance, I'll just use x. And then if this is very, very thin, I think that's going to make a difference.
So that would be area of interaction?
Yes, area. So I'm going to, for all of my calculations, I'm going to assume that the area is constant.
Okay.
And I'm going to assume that the temperature drops linearly. That's a pretty good estimate.
Okay.
So let's double check my formulas. Yeah. So Q dot right here.
And Q dot is
Heat transfer rate.
okay.
So how fast heat is moving.
Right underneath that.
Yeah. So that's what the dot means by the rate. I'll just say kilojoules per second. How's that? So that's rate. So it's equal to a constant based on the material. The constant technically depends on temperature, but usually you assume it's constant just for simplicity. Multiplied by the area. So if the area increases, then you can get more heat transfer going through it. Then that's multiplied by the change in temperature over the change in position, basically. If you just want to go, if you want to simplify it a little bit, you just say T over the distance, because you care about the total distance. If you wanted to find it at a different distance, you would just make that smaller. But, so let's do an example. So let's say this is 1 meter long, and the area is let's see, 0.01 meter squared. Just to make it simple. 1 meter, and then the difference across that is say 50K maybe. I need to look up the can't remember if it's called heat conduction or it's a property of the material. You can look it up. K is the thermal conductivity. So you can look these up in tables based on the material. The units of this are in watts per meter Kelvin. Being joules per meter Kelvin second. If these things are not constant, if the area increases one direction, or if the temperature is slowly dropping, or if the area is weird or something,
Okay.
then
The area of one plate compared to the other is different?
the area that it's passing through.
Oh.
You care about this area. And we're assuming that the area is constant here, or the area here is the same as the area here, and the same as the area here. It's an important thing to recognize. If, for example, the shape looked more like this, then you could not assume constant area.
Okay. You have to vary that with whatever shape you're working with.
Yeah, so heat is going to be able to move faster through here because the area is increasing. And you could calculate this, but you'd need some calculus, basically.
Gotcha.
Now, if you're not doing something simple like constant transfer rate, you probably want to use a program to calculate it. It's going to be pretty complicated.
And which programs or software would you suggest for doing?
SolidWorks is decent, it's not perfect. I would probably go through some of the equations and see how this is derived as a constant. They'll have like integrals and stuff. So, for example, aluminum, we can assume is about 200 watts per meter Kelvin. So, bring that up to here. We say heat transfer rate between the two plates is K, 200 watts per meter Kelvin, times the area, which is 0.01 meters squared, times change in temperature, which is
That would be between the two plates, correct?
between the places you're assuming, divided by the distance between them, which is 1 meter.
That's why a larger distance would be more energy applied, or higher rate.
Lower, you would need to apply more energy to get it move faster.
So lower the rate then.
Yeah, so if it's longer, then it takes more time to get through, so it's harder for it to get through. But if the area is larger, then it has more room to move through. Kind of like if you're trying to walk across a room. If the room is longer, it takes you more time, it's harder to get there. If the room is narrower, it might be harder, it's slower, whereas if it's open and wide, you can get more people through it, basically.
Oh.
But so we see meter squared here, and then two 1 meters, so those cancel out, and Kelvin cancels out. So we get, let's see, it's 2 times 50, that's 100 watts. So 100 joules per second. Transferring across that rod. It's not a ton of heat, which is what do you expect with a 1 meter long rod? It's pretty thin. As you can see, all these, the conductivity, area, and the temperature are all just linear relations. So if you double them, then you double the heat transfer rate. And this one, this one is a 1/over relationship. So it can go to either infinitely if it's tiny, or approach to 0 if it's super long.
Does this change if the source of heat is different? Like if the source of heat is from like photons hitting it, or the source of heat is
only
something that's being
only from the surfaces. So
okay.
You're saying what happens in between the surfaces of a solid.
So that's what we're measuring here.
Yes. So you know the temperature of the surface is all. It doesn't matter what happens on either side because we already know the temperature difference. But you may not know the temperature difference, which is why we need to bring other stuff like radiation and convection into it. Yeah, so for example, if I had, like you previously discussed, a coffee mug, I'm just going to draw one side of the coffee mug. You have convection heating up one side of the coffee mug, and that's going to make the coffee right on the edge not quite as hot as the stuff in the middle, because heat is transferring through it, because the mug will have cooled down this stuff a little bit as the mug heated up. So you won't know exactly what the temperature right at the edge is. But if you did know, then you could just use this, and it's really, really easy, just a linear relationship, and easy to do. I'm going to jump onto convection real fast.
Sure.
Well, actually, I'm not going to do any convection. We're not going to use any convection for our stuff.
Oh yeah, we are in space.
Space.
Not a lot of convection going on out there.
Yeah, so the only convection is going to be inside the habitat between the sides, but it's such a small space, and the gas will have such a low thermal mass that I'm just going to ignore it. Which is good, because convection can be very, very complicated. When you take Intro to Thermodynamics, or just engineering thermodynamics, they're going to give you a value, and they just say it is the convection coefficient. I can't remember what it's called, or something like that. Even though in reality, you're going to have to go through a whole bunch of things to try to figure out what that coefficient is. So I'll just give you the formula real fast.
Sure.
Yes. Okay. So we have a heat transfer coefficient, and you may ask, well, what does that depend on? It depends on a lot of things, and we're not going to go into it.
Okay.
It depends on whether the convection is forced or natural. It depends on considerably more on the temperature of the gas than conduction matter. It's going to depend on the surface and what the friction is on the surface, and a whole bunch of other things. It's a fucking mess. but I'll give it to you anyways. So if it's a difference in temperature, let's assume you have a wall. Let's assume we know the wall temperature, we have a thermocouple on it. Let's see. So that's 300 Kelvin, and we know that the ambient air temperature is 275 Kelvin. So the difference in temperature is between the middle of the stream, or the average gas temperature, and the surface you care about. So the temperature is going to be something like that. So you can see this is not a linear relationship with distance. That's because we didn't include any distance in the formula. And this is a surface phenomenon, basically. We're assuming it's a surface phenomenon. You can also assume it's a phenomenon just in the gas, between two different points in the gas. But generally, you assume that the gas temperature, you just call that T infinity. So assume it's like infinitely far away, and it's not moving or anything like that.
Now you mentioned density drives, or change in density drives this process.
Yes.
How come it's not accounted for in the equation, or is that accounted for in H?
Yep, it's an H.
Oh, okay.
There's the type of fluid matters, the pressure and density of it matter. Everything matters. This is why this is a fucking pain in the ass.
Good to know.
Like you can do a whole bunch of grad work just trying to figure out this for certain places, and their estimates, they're not usually very good. You can talk about like mass error bars. This also has to do with the way gas flows as it's hitting a surface. It differs depending on how fast the gas is moving. So you can have turbulent gas or laminar, which is just straight. Turbulent is like it's mixing itself a lot and stuff. It's a pain in the ass. For 301, they're just going to give you most of the simple stuff. When you get into heat transfer and fluid dynamics courses, you're going to get more into this. They're still going to simplify it a lot.
Got it.
Just keep in mind that it's complicated. I think that's all we want to say on convection.
All right.
For the most, we don't care about it. Now, we'll care a little bit when we're inside the fairing, and we're still in the atmosphere. But I think honestly they can just give us they're going to give us a heat transfer rate. I'm not going to worry about it.